Okay, alright, so today we're going to be discussing two theorems, Green's theorem and the isoperimetric inequality. So, to begin, we're going to have some definitions. So if we talk about a vector field, on an open set, a vector field is essentially a smooth function, which we'll call f, from U to Rn. So essentially what that means is, let's say we're in R2 and we're having a vector field on this space. That means for every point in U, there's maybe like something like that. Every point in U is assigned a point in Rn. So you can imagine it as like a field of arrows, which is how people usually think of vector fields. And furthermore, when we get to things called fiber bundles, this is not for a long while, but I figure I'd just talk about it. Vector fields we can generalize them into things called sections. So that's a little bit about vector fields. Now let's talk about the line integral. So let's say we have a plane curve C parametrized by gamma from AB to R2, and F is a vector field whose domain contains C. Then we define the line integral like so, and it is essentially the integral from A to B of the inner product of f of gamma of t and gamma prime of t, with dt as the differential. So if C is closed, then we write the integral with a funky looking circle. And by the way, this is one of my favorite symbols in mathematics. I just really like it. I don't know why. And we call it the circulation of F around C. So that's basically a little bit about line integrals, and now let's talk about the gradient. I know there's a lot of definitions going on, but we'll talk about some other things soon. So let's say we have a function from U to O, where U is an open set. The gradient is denoted by nabla f, and it's a vector field, and we can basically think of it as, let's say we're in, and its ith component function, I guess you can define it as the partial derivative of f with respect to the ith input variable. So if we're in R2, if this is R2, I'm saying, then the gradient of f is going to be partial derivative of f with respect to x, and then the partial derivative of f with respect to y. If we're in R3, then the gradient is partial derivative of x with respect to x, f with respect to y, and f with respect to z. So vector field F is called conservative if it is the gradient of some smooth function f on the open set U. So if f equals the gradient of f. In this case, we call f a potential function. So our first lemma for today, if we have an open set and f is smooth, and gamma is a regular curve, then the derivative of f of gamma of t is equal to the inner product of the gradient of f of gamma of t and gamma prime of t. Furthermore, a very related concept to this is the directional derivative, which we're going to denote as df in the direction of the vector p naught of v naught. Which is simply this. So we come to a proposition now. If we have an open set U in Rn, and we have a smooth function and this gamma, the curve it parametrizes is piecewise regular and oriented, then the line integral of the gradient of f and d gamma is equal to this. Furthermore, the line integral is considered to be path independent. Because no matter which curve we take, the answer is always going to be f of gamma b minus f of gamma of a, so long as the start and end of the curve are at the same places. So the proof for this is pretty short. So we start out with this expression, and by the definition of a line integral, we have gradient of f, gamma of t, gamma prime of t, dt. And by our lemma from before, we have ab d over dt, f of gamma of t, dt. And by the fundamental theorem of calculus, we have f of gamma of b minus f of gamma of a. And that is simply our proof for this proposition. I'm going to talk about another proposition which I will not prove. So these are equivalent properties. So remember, if one of them is true, all of them are true. So if we suppose a vector field F is conservative, then the closed line integral of F will always be equal to 0, no matter which curve. So long as it's closed, it's going to be 0. Furthermore, the line integral of F is going to be path independent, as defined above. So now we get to the infinitesimal circulation. And if we have a vector field PQ, and this is a two-dimensional vector field, then the infinitesimal circulation is going to be the derivative of Q with respect to X minus the derivative of P with respect to Y. So keep in mind this notation is basically this. So now let's look at one very important theorem in multivariable calculus, and it is called Green's theorem. So, if C is a positively oriented and piecewise regular, simple, closed curve, and that's a lot of descriptions, and it's in the plane. Suppose D is the interior of C, and F is a vector field defined appropriately, that is, on the union of D and C. Then we have that this formula holds true. So this is called the double integral, and when we see a double integral, usually there's going to be like two variables, but sometimes you might see dA. The calculation of double integrals for our purposes isn't going to be very important. This is not multivariable calculus, so we're not going to be computing double integrals like, Alright, so there's a corollary that follows from this. 2 point, oh, well, that's in the book, but. So, if we have a curve that is the counterclockwise circle of radius r centered at P, then the infinitesimal circulation at P is equal to the limit as r approaches 0 of 1 over pi r squared times the closed line integral of f. So before we prove Green's theorem, let's prove this very quickly. So if R is sufficiently small, then the infinitesimal circulation is approximately constant. So we have, by Green's theorem, and if we have that this is constant, then we can basically take that out and compute. This basically means the area, so we get qx minus py, and this is a p, times the area of dr, and the area is pi r squared, so it follows that as we take the limit, this holds. So now we prove Green's theorem. Proof of Green's theorem. So we're only going to prove it when we have a rectangle. So when a closed curve is a rectangle. So we're going to call this one CL, CB, CR, and CT. Top, right, bottom, left. So if we want to travel counterclockwise, starting from here, we go along CB, then along CR, then opposite from CT, and then opposite from CL. So the integral along CB of f is equal to AB f gamma t, gamma prime t, dt equals and note that because we're traveling along here, gamma prime is just going to be the unit vector in the x direction. So there's that. And that is basically like so. So that's our first one. I'm not going to compute all of them, but I will say for CR we have yeah, I think this is it. For this one, along CT, not negative CT, we have, and then along CL, we have this would be CD. and this should be CD. Now you might be wondering, why exactly do I have all these random T's, C, B, A, D? The reason why is because I forgot to mention this. I'm getting sloppy, but we have these. So along CB, for example, C is going to be the Y value, so we put C in here. Along CR, B is going to be the X value, so we put B there, and so on and so forth. And you can see here, along CB, we're integrating from t equals A to t equals B, which is basically y equals A, or x equals A to x equals B. And then so on and so forth. So if we combine all these, and don't forget the negative signs for them, we get that the total integral along the curve is equal to this plus this. Meanwhile, so keep this in mind. Meanwhile, if we take the double integral of qx minus py dA, we can split this up just like we would for a single integral, except there's two of them. And then notice that the area is essentially the rectangle. So first we integrate from A to B, and then we take all that, and then we integrate all that from C to D. I'm not sure if this visualization makes much sense, but hopefully that should clarify why I'm doing what I am. But this is not multivariable calculus, so I'm only going to just dive briefly into this. So dy minus AB CD and notice that, remember, this is and notice that this is the partial derivative of q with respect to x. So we keep that, but this becomes I think I'm doing this right. Yeah, q, and from b to a, which is basically this. It's just different notation. I'm minus p from c to d, like that. And since these two are equivalent, therefore it follows that this is equal to this. And therefore Green's theorem has been proven. Now, a couple of more definitions. We define flux of a vector field F across a curve C as flux equals the inner product with the normal vector times the magnitude of the speed delta t. So let's say we have a vector field. I'm just going to create one where it's going outward. And we got a curve something like this. At each point, we're going to take the inner product of the vector field with the normal vector, which I'm drawing in green, and then multiplying that by the magnitude of the velocity of the curve's parametrization. We can also calculate the divergence of vector field, and it is simply just the partial derivative of p with respect to x plus the partial derivative of q with respect to y. And there is a flux version of Green's theorem. So if we have a flux across a closed curve, then that equals the double integral of the interior of the curve of the divergence. So I'm going to go over the proof very quickly because I also have to get to the isoperimetric inequality, but I will go over the proof. So we can consider the normal vector as before as a sort of rotation of the velocity, and this time it's going to be negative. So remember, the velocity is x prime, y prime. That's how we parametrize it. So the normal vector we parametrize as y prime negative x prime. So the flux we have defined as the integral of the inner product of f of gamma of t with the unit normal dt. And if we expand, that is going to be equal to p of gamma of t, q of gamma of t, and then y prime of t, negative x prime of t, dt. However, if we rearrange the inner product, the terms of the inner product, if we swap the terms like this, and then put the negative over here, we get negative q gamma of t, p of gamma of t, and then x prime of t, y prime of t, dt. So let's call this a second f of gamma of t with like a tilde on the top. And we can define this as a sort of line integral because we have a vector field and its velocity. And furthermore, by the definition of a line integral, we can write a previous expression like so, and then applying Green's theorem, we take this, the second term, and partial derivative of it with x, so px, minus q, the partial derivative with respect to y, so that's a plus because two minus signs cancel out, and we get qy dA. And therefore, the flux version of Green's theorem has been proven. So before we begin our discussion on the isoperimetric inequality, we're going to look at a corollary of Green's theorem. So if we have a closed curve with interior D, then the area of D equals, and the curve is parametrized like so, T is in A to B. So A to B makes more sense here, of x of t, y prime of t dt, which is equal to the negative of a, the integral from a to b, of y of t, x prime of t dt. And the way you prove this, I'm not going to do the whole working out of it, but you apply Green's theorem to the vector field, this vector field, and then you apply Green's theorem to these two, and then you should come out with similar results. So now we reach the isoperimetric inequality. Isoperimetric inequality. So let's say C is a simple closed plane curve. So if we have L, the length of C, and A, the area of the interior, then L squared is greater than or equal to 4 pi A, and it is equal if and only if C is a circle. So the first part of our proof is a little geometric. So let's say we have a curve like so. We're going to take vertical lines and move them in such a way so that both of them are tangent to the curve. Furthermore, we're also going to create a circle that is, oh, this is badly drawn, that is also tangent to both. So we have gamma. We're going to make this point gamma of 0, and we're going to make this point gamma of t0. We're going to create another function just for this circle, S1, beta, so this is going to be beta 0, and this is going to be beta t0. So with that in mind, if we suppose we have a gamma t equals x of t, y of t, we want these two parametrizations of the curve and the circle to sort of line up with each other, if that makes sense. So what we do is we're going to say beta of t equals x of t, y tilde of t, where y tilde of t equals positive or negative r squared minus x of t squared. So, what is the area of C? The area of C, so we're going to write this as A, and by our corollary here, so now that we're seeing why Green's theorem is important for this video, we're using it to help prove the isoperimetric inequality. We're going to take it from the length 0 to L of x of t, y prime of t, dt. I forgot to mention, this curve is parametrized by arc length. Parametrized by arc length. So, we have that, and the area of the circle is going to be pi r squared, where this is r, this is r, and that is basically the negative of 0 to L of y tilde of t, x prime t, dt. So, if we put these two together, then a plus pi r squared is equal to the integral from 0 to L of x y prime minus y tilde x prime dt. And this is going to be less than or equal to the integral of the same thing, but with the absolute value. Which is essentially the square root of this squared. So if we expand this outwards, or if we expand the expression in the square root, then we get x squared y prime squared minus 2x y prime y tilde x prime plus y tilde squared x prime squared dt. And we can actually arrange this algebraically as x squared plus y tilde squared times x prime squared plus y prime squared minus x times x prime plus y tilde y prime squared dt. And because this is always going to be non-negative and this negative sign exists, we can create another inequality. This is going to be less than or equal to the integral without that minus term. So we have x squared plus y tilde squared x prime squared plus y prime squared dt. But remember, we parametrized by arc length, so this is going to be equal to 1. So we have x squared plus y tilde squared dt. And remember how we parametrized beta, which is the circle. This is going to be equal to the magnitude of beta, which from 0 to L, which is basically the integral from 0 to L of r dt. Oh, I forgot the dt over here, which is L times r. So a plus pi r squared, let me put that over here, a plus pi r squared is less than or equal to LR. So furthermore, the geometric mean, which is basically going to be the square root of a times the square root of pi r squared, is going to be less than or equal to, the geometric mean is always less than or equal to the arithmetic mean. So the arithmetic mean would be 1/2 a plus pi r squared, which is less than or equal to 1/2 LR. If we square this side and this side, we get a times pi r squared is less than or equal to 1/2 LR. And if we flip the inequality around and do a little bit of this, multiply by 2, or this should be 1/4 L squared R squared. That's my bad. So we get L squared is greater than or equal to 4a pi, as we desired. So I think this video is getting a little bit long, so I might not discuss the equality case, but what we can say is that we can eventually say that beta prime of t equals gamma prime of t. So that implies that gamma equals beta plus w for some constant w, which means it's a translation of the circle. And this is if and only if equality holds. So that's a little bit about Green's theorem and a little bit about the isoperimetric inequality. Thank you guys for listening, and I'll see you guys in the next video.